You're traveling to an abandoned research outpost where your team believes scientists unlocked the secrets of sustainable energy. You think this secret is connected to nuclear science. But unfortunately, on your journey to the outpost, you lost your nuclear expert. Your expert was going to activate a fission reactor, but now it's down to you and Dr. 1 to learn the science of fission to activate the reactor. Succeed, and you can spread your new knowledge of sustainable energy. Fail, and you may be stuck on this planet.
Hi there, welcome to this abandoned labster outpost. I had a quick look around the outpost, and I think the key to activating this fission reactor is answering the security questions on the control panels. The questions are all related to fission, so you will need to become our new nuclear expert in order to turn on this reactor. But before we get started, let's get you oriented with your lab pad. This simulation uses voiceovers. If you don't have audio, click the speaker symbol on the top right of your lab pad to switch the play mode. If you disable the sound effects, the lab pad will slide up whenever there are instructions to read. You can select what type of audio you prefer, such as music, sound effect, and voice. Deselecting any of the options will mute that option. Click Continue to learn how to navigate through your mission. Using the lab pad is an important way to get the most out of this simulation. Is this the first time you've played a labster simulation? Perfect, then let's get started with your first mission. Our first mission is to activate the reactor's startup sequence. It is unfortunate that our nuclear expert is not here, but on the journey, they did talk to me about the fission reactor. They told me that fission is similar to radioactive decay because both processes take place in the nucleus of an atom. I think it would be a good idea to make sure you are familiar with the atom and radioactive decay before we start pressing any unknown buttons. So I am going to ask you a few questions to check what you already know, and I'll help you along the way. Since I'll be talking about the atom, let's go look at that atom over there. Go to the hollow table with the atom. This is an atom of the element beryllium. It has a nucleus in the center made of 4 protons and 5 neutrons. 4 electrons orbit the nucleus. Since protons and neutrons are found in the nucleus of the atom, they are called nucleons. The nuclear expert taught me that every nucleus has a mass number and atomic number. The beryllium nucleus in front of you has a mass number of 9 and an atomic number of 4. What does the mass number describe? That's right, the mass number is the total number of protons and neutrons. What would you like to do next? The atom is described by 2 numbers, the mass number and the atomic number. The mass number represents the total number of protons and neutrons. The atomic number is the total number of protons. The beryllium nucleus in front of you is stable because its mass number is 9. But if the nucleus had a mass number of 10, it would be unstable. Most nuclei prefer to be stable, so an unstable beryllium nucleus might undergo radioactive decay to become stable. Different types of radioactive decay release different materials. Do you know what type of radioactive decay would release an electron to make the beryllium nucleus more stable? That's right, beta decay releases an electron. An unstable beryllium nucleus would undergo beta decay to become a stable boron nucleus. What would you like to do next? Radioactive decay is a process where an unstable nucleus ejects material to become stable. The 3 types of radioactive decay are alpha, beta, and gamma. All types of radioactive decay can be expressed as an equation. The mass number and atomic number appear in these equations before the element symbol. Impressive, you'll be a nuclear expert in no time. I am sure we will get the reactor running and share our knowledge with Earth. Let's go take a look at the reactor. Go to the control panel and look at the reactor through the window. Wow, it looks like the reactor core lowers into that glass tube when we start the reactor. To start up the reactor, we need to answer the security question on this control panel. Let's give it a go and see what happens. You are correct. During alpha decay, an unstable nucleus releases an alpha particle to become more stable. An alpha particle is the same as a helium nucleus. Door unlocked. Reactor start sequence engaged. That sound must be the reactor. And look, the reactor core lowered down a bit. Let's go to the next room where we can get the reactor online. Go to the next room to continue activating the reactor. Look, there is a security question on that control panel. The reactor security question asks, what happens when we fire a neutron at a uranium nucleus? If we answer this question, then we will activate one of the 3 reactor modules. Let's take a look around the room to find clues about the answer. Go to the glowing hollow table in the middle of the room. This hollow table is zoomed in on the nucleus of a uranium atom. This is the same nucleus mentioned in the security question on the control panel. Let's press the Fire Neutron button to see what happens. Click the Fire Neutron button to find the answer to the security question. Wow! We fired a neutron at the uranium nucleus. The nucleus split into 2 smaller daughter nuclei and released some neutrons. On the screen, we can see that this process also released some energy. Let's see how much energy this process can generate by following the neutrons. Click on the neutron you want to follow. Click the button to fire the neutron at another nucleus. Look at the screen, the energy increase was much greater this time. The diagram shows that both the neutrons generated in the first split went on to split another uranium nucleus. That must be why the energy generated is so much more. If we follow the neutrons once more, what would happen to the energy? Let's see if your guess is correct by following a neutron again. Click on the neutron you want to follow. Click the button to fire the neutron at another nucleus. Amazing! The energy just keeps going up and up. By starting this chain reaction, we could have a fantastic source of sustainable energy. Your guess that the energy would be even greater was correct. I think we have enough information to answer the security question on the control panel. Go to the control panel to answer the security question. You are correct. Fission is a process where an unstable nucleus splits into 2 smaller daughter nuclei and neutrons and energy are released. Door unlocked. Reactor module activated. Look, the reactor core lowered a little bit more. Only 2 more reactor modules to activate. Go to the next room to continue activating the reactor. The reactor security question asks us to balance the fission equations. To understand how to do this, we should look for clues. Then we can activate the second reactor module. There is a theory station on the other side of the room displaying an equation for fission. Maybe it can help us balance the equation? Let's go there to find out more. Go to the theory station to learn more about fission. At this theory station, you can toggle between the particle image of fission and the nuclide equation of fission. Click on the toggle to switch between the particle image and the nuclide equation. Also, you can listen to the text on a page by clicking the Read Aloud button. Click on the Read Aloud button to listen to the text on the page. A slow-moving neutron is fired at uranium-235 and is absorbed to make uranium-236. Finally, you can flick through the stages of fission with the arrow buttons. Click on the right arrow to turn to the next page. Now you know how to navigate the theory station. Let's see what clues you can find to help us balance the equations. Use the buttons to explore the pages. Try to find information that can help you balance fission equations. Then raise your lab pad to answer a few questions. I noticed some interesting information when reading those pages. Did you notice it too? Toggle to see the nuclide image on the theory station. What do you notice about the total atomic number before and after fission? Sharp work! That's what I noticed too. The total atomic number before and after fission is the same. This isn't true for all nuclear chemistry though. For example, in beta decay, the total atomic number will differ before and after the decay. This image shows how we can calculate the total atomic number before and after fission. Toggle to see the nuclide image on the theory station. What do you notice about the total mass number before and after fission? Spot on, the total mass number stayed the same too. This image shows how we can calculate the total mass number before and after fission. So, the total mass number and total atomic number are the same before and after fission. This will help us to balance the equations. Let's go to the control panel and attempt the security question. Go to the control panel to answer the security question. To balance the equation, you need to select numbers from the drop-downs. Selecting a number can change either the mass number or the atomic number. Remember, the mass number is the top number next to the element and the atomic number is the bottom number. Click the drop-down next to zirconium, and select a number. You change the total atomic number of the products, and that number has changed at the bottom of the screen. The total atomic number before and after fission should be the same. Click the drop-down next to xenon, and select a number. This time, you change the total mass number of the products, and that number has changed at the bottom of the screen. The total mass number before and after fission should be the same. Select numbers from the drop-downs that balance the equation, then click the Submit button to... Great work, you balanced the first equation. You can see that the total mass number of the products is equal to the reactants. The same is true for the atomic number. You have two more equations. Balance the total mass number and total atomic number on both sides of the equation. Amazing! Interestingly, the xenon in this equation had a different mass number from the previous equation. That's because they are isotopes of xenon. You only have one more equation to balance. Balance the total mass number and total atomic number on both sides of the equation. Brilliant! You balanced all the equations. Each equation featured a different nucleus undergoing fission. These are commonly used in nuclear power plants. Great work! You activated another reactor module. There is only one more reactor module to activate. Let's keep going. Go to the next room to continue activating the reactor. The security question on the control panel asks, what part of the fission process is the most radioactive? Let's go to the hollow table to find out more. Go to the hollow table to learn more about fission and This hollow table is similar to the one we saw earlier because it is displaying a uranium nucleus. However, the screens seem a bit different. Let's press the button to see what happens. Click the Start button and observe what happens to the radioactivity. Look at the screen. It shows that the radioactivity of the fission products is greater than the uranium nucleus. I wonder if the radioactivity will increase again? Let's press the button again. Click the Fast Forward button and observe what happens to the radioactivity. That's interesting. The fission products decayed to become more stable nuclei. On the screen, we can see that the radioactivity decreased, which makes sense because the nuclei are more stable after decay. What type of decay do you think we observed? Yes, I think it was beta decay too. We saw an electron being ejected and a neutron changed to a proton. The radioactivity decreased this time, but we don't know if the trend will continue. Click the Fast Forward button and observe what happens to the radioactivity. Our trend continues. The nucleus decayed again and the radioactivity decreased too. This decay took slightly longer than the last one. The nucleus might be more stable than before, but it is still a bit unstable. Do you think the radioactivity will decrease again when we press the button? Let's observe what happens to see if you are correct. Click the fast forward button and observe what happens to the radioactivity. Phew, that decay took a lot longer, almost a year. Luckily, we had this time skip button, so we didn't have to wait. Your prediction was correct. The radioactivity decreased again and the nucleus is more stable than before. I think we both know what is going to happen to the radioactivity from now, but let's complete the decay chain and get to a stable nucleus before answering the security question. Click the fast forward button to get to a stable element. This decay was a bit shorter than the last one. I think there is still a bit left to go before we get to a stable nucleus. So let's keep going. Click the fast forward button to get to a stable element. This decay took a very long time, 2.29 times 10 to the 15 years. At least we finally reached a stable nucleus. Interestingly, this time we observed an alpha decay and not a beta decay. We can clearly see the trend in radioactivity, so we can easily answer the security question on the control panel. Go to the control panel to answer the security question. You are correct. The fission products are more radioactive than the initial nucleus and the nuclei they become after decaying. Door unlocked. Reactor module activated. Great. I think we have activated all the reactor modules. Hopefully it will just be a simple flick of a switch to turn on the reactor. Go to the next room to turn on the reactor. Look, a lever next to a control panel. Maybe that's our on switch? Let's check it out. Go to the control panel to turn on the reactor. We can see through the window that the reactor core has fully lowered. It is ready to turn on. This was only possible because you answered all the security questions. You discovered what happens during fission and how it produces so much energy. You learned that the mass number and atomic number are conserved in fission and used this knowledge to balance fission equations. And, you investigated how the radioactivity changes before and after fission. Before you return to Earth, is there anything else on your mind? As you have learned in this sim, nuclear fission is where the unstable nucleus of an atom splits, releasing excess energy and neutrons in the process. In nuclear fusion, the nucleus of two atoms fuses together, releasing excess energy and neutrons in the process. You can learn more about this in the fusion sim. Before you return to Earth, is there anything else on your mind? In this sim, we learned that nuclear fission reactions could produce low-carbon sustainable energy. This could generate power for our homes and businesses, even vehicles like submarines. For example, submarines powered by nuclear fission can operate for months or even years without refueling, making them ideal for long-range missions and extended sea patrols. This is great for marine or polar exploration and guarding our seas. Before you return to Earth, is there anything else on your mind? I can be powered by many different sources, from batteries to solar, or even plugged into the lab pad. This all depends on where we are doing our science experiments. Before you return to Earth, is there anything else on your mind? Now all you need to do is pull the lever. Amazing! Without you becoming a nuclear expert, we could have never turned on this reactor. Now we can take our knowledge of sustainable energy back to Earth.
Thanks to your efforts, the mission is a success. On your way home, you find your nuclear expert in space. Now the team has two. Your team is excited to share their knowledge of sustainable energy with Earth.
Let me ask you one last question. Do you feel like you gained relevant knowledge during this simulation? Thank you for your feedback. Your score has been saved together with your 100% progress. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now.